So welcome everyone. We're very happy today to have Nina giving us a talk on physics-informed neural networks. Before I turn it over though, a little bit of housekeeping. The middle QR code you see on your screen will take you to the GitHub link for the entire tutorial series. The materials that you need for today are under the folder that starts with today's date. If you are not already a member of GDS, the American Physical Society topical group on data science, I would recommend you to go ahead and join if you do find these tutorials to be useful. If you are already an APS member, then adding GDS as a unit will only cost an additional $10. And you can join GDS using the link on the right side of the screen. If you have attended more than one of these tutorials and you think you have some feedback as to how we could improve these, or if there's something that you think we're doing well and you want to make sure we continue, please provide that to us anonymously using the QR code on the left side of the screen. If you have any suggestions for future topics you'd like to see covered in these tutorials, or if you have nominations for speakers you would like to see in future tutorials, even if they're self-nominations, please send me an email at the email address on the screen, and we'll make sure we get those topics and speakers added to our schedule. Our next tutorial will be in 2 weeks on July 11th at 1 p.m. Eastern. The topic will be modern Python tools for reproducible science, where the speaker will be giving us a talk on alternatives to Jupyter notebooks and other common libraries, which allow you to both speed up your codes and make them look nice and be reproducible. If you're new to this tutorial series and want to go back through the previous tutorials, all of them are recorded and posted on the APS YouTube channel. You can access the playlist at this QR code, and all the materials for the previous tutorials are also linked in the description and on the same GitHub as the materials for today. And yes, I'll be putting all the links in the chat after I'm done. Finally, as an announcement, GDS has started a paper highlight series. So if you're a graduate student, postdoc, or early career member, and you've recently published a paper that you think would benefit the data science community at large, please scan this QR code and fill out the short form. We would love to highlight your work both on our webpage and also on our social media accounts. And so with that, I will go ahead and turn it over to Nina.
Thanks, Julie. All right, I'll go ahead and share my screen. Okay, and I just want to make sure that everyone can see sort of the GitHub repo. This. So,
Yes.
Okay, thank you. All right, so today's tutorial is going to be kind of like a compare and contrast of two main classes of what's known as scientific machine learning methods. One of them is physics-informed neural networks, and the other are neural differential equations. And they're kind of like complementary techniques in a way. So this entire tutorial is in like a Jupyter notebook style format, and you can run everything on Google Colab if you have a Google account. So there's actually this like badge here that you can click on that should send you right to the notebook. So if you're following along, please go ahead and do that. And before I like launch into the introduction and everything, I'm just gonna have everyone run a few kind of setup cells so that can get set up while we're talking about sort of the intro material. So if you want to go to the runtime and just change the runtime type to GPU, since training models is usually better on GPU, can hit that and hit save. And then we're just going to run these first two cells, which is just going to be installing some packages that aren't default to the Google Colab and also cloning our repository so we have access to all the files. All right, so just take a moment to see if is everyone like okay with those first few setup steps. All right, so then let me begin with just a brief introduction of sort of the topics that we'll be looking at today. So as I mentioned, this tutorial is on scientific machine learning. Let me just make this a little bigger. So what is scientific machine learning? So it's like a combination of methodologies from machine learning, which are usually, we think about like implementing a neural network that's going to approximate some function that, it is hard to model otherwise. And it also combines methods from scientific computing, which are things like numerical integration or differentiation and things like that. And the reason we might want to do this is that sometimes when we're crafting models to represent some physical systems, we have some domain knowledge or we have some, assumptions about what those models should do and some physical laws that they might need to obey. But we don't necessarily have the models themselves, and we instead have data that we can use to train a machine learning model to approximate them. And so they're kind of a combination of both being data-driven as well as domain-aware to a certain degree. So scientific machine learning is kind of trying to blend the best of both worlds in a way by being flexible in the sense that machine learning models are flexible and expressive to represent different functions, but they're also a little bit more interpretable because we're sort of imbuing this kind of bias of some physical laws that we expect. So as I mentioned, this tutorial is kind of a compare and contrast between two popular approaches within kind of this broader umbrella of scientific ML. So here I kind of put together like a chart to try and illustrate the differences and also delineate the different use cases where these types of approaches are appropriate. So the first column and the first topic I'll discuss are neural differential equations or neural ordinary differential equations, also partial differential equations. There's ways to kind of model a wide variety. So when might this be appropriate? So this type of approach is needed when the dynamical model that we're interested in is unknown. And so we actually use a neural network to approximate the differential equation itself. So how do we train this model? Well, the assumption is that we actually have some samples of observations in the solution space of this differential equation. So like we have samples of, in this case, what is rho as a function of x and t at some discrete points. But we don't exactly know the underlying differential equation that led to those solutions. And the way that we're going to train that type of network is we actually numerically integrate it during the training process from a set of initial conditions. We could potentially have multiple trajectories that we've observed, and we could feed all of them in as long as they all obey the same underlying differential equation. And then we're going to compare this numerically integrated prediction that the neural network gives us with what these discrete solutions are at the available points. And that's what we'll use to kind of to update the weights of the neural network and try to learn what that equation is. All right, so then on the other hand, we have physics-informed neural networks or PINs. And the reason that I say they're kind of complementary is that in this case, the thing that we know is actually this differential equation. So we might have a system where, we kind of know, oh, this is some type of like a reaction diffusion system, and we have an equation to model it, but it's too complicated to integrate. So like using a numerical solver might be extremely costly or challenging. And so what we might want to do instead is model that solution with a neural network. So we don't have to go about actually numerically integrating this. This is a little bit more restrictive than a neural ODE in the sense that we have to fix the initial and boundary conditions that we're modeling. So it's the neural network will just like be modeling one single solution to this differential equation. But it's also flexible in that, it can then allow us to evaluate that solution at arbitrary points in our domain. And that will become clear, I think, when we go through the code. So given some initial condition and some boundary conditions, we can use a neural network here to model the solution, as we said, and circumvent the whole like integration process. And then this solution will be a function essentially that we can evaluate at arbitrary sort of values, let's say in the spatial dimension, and potentially even kind of extrapolated a little further in time. Okay, so that's kind of the brief overview of what these two techniques are. Are there any questions at this point, sort of the basic ideas behind these two approaches? All right, if not, then I'll kind of keep going forward here. So just to give you guys an overview of what libraries we'll be using here. So all of this I implemented with the PyTorch library. Are people here familiar with PyTorch or TensorFlow? Great. So this will be done using PyTorch, and so we'll need that to, for instance, do automatic differentiation, which is essential particularly for the pins. And we'll also use one additional library when doing the neural ODE example, which is Torch DiffyQ. It's just a library of ODE solvers that's been implemented in PyTorch so that we can do that numerical integration when solving the neural ODE. And to develop this tutorial, I borrowed examples from the original papers that introduced the neural ODE and pin concepts. So this paper here is kind of the paper that introduced neural ODEs. And then the second paper is another one that I thought was particularly illuminating in talking about neural ODEs and PDEs. And then finally, this is the original paper that introduced pins. So I highly recommend looking into these resources more for additional details. Okay, so hopefully all of these things have now installed. As I mentioned, we're just cloning our repo here to get access to all of the files, and then we're installing additional packages. This is Torch DiffyQ. This is just some like color maps that I think are helpful for visualizing things. So it's not necessary, but just something that I like to use. Okay, so here's mainly all of our imports that we need. So as I mentioned, we're using PyTorch, and then we're going to import this ODE like integrator from Torch DiffyQ. I do have a utils script that has a few kind of helper functions that didn't want to clutter the notebook with, but they're all listed out here. So if you are curious about like, oh, what did this function do? Mainly they're for visualization, and this one I'll talk a little bit more about. It's just how we are gonna get batches for training. But you can find them all in the repo as well. Yeah, it should be here too, but just in case you need to refer to that, they're all found in the utils. So let's go ahead and run that. And so for part one, I'll introduce the neural differential equations. So as we saw before, we're going to have a neural network. Here, let's call it f of theta, where theta are the trainable weights. We're going to have that approximate some differential equation, dy dt. And the basic steps for kind of approaching this is, so we define this neural network, and then at each iteration, we integrate it with respect to time, starting from some initial condition, y0, which will be given, to get a prediction of that trajectory further for some set of discrete time points that we've chosen. And that prediction is then compared to the available points in the solution space using a loss function of choice, here just mean squared error. And then we similarly backpropagate and optimize the weights. The kind of special thing, because you'll notice that the weird thing that we're kind of doing here is a numerical integration of a neural network, which is not something that we typically need to do. And that actually can be quite expensive when you think about back propagating through the internals of the solvers. So for more kind of complex solvers, that is not really a good thing to do. It can be pretty both memory intensive and kind of numerically unstable to think about back propagating through that. And so the paper that introduced neural ODEs proposes using the adjoint method, which is something that you can, that is directly implemented in this library and you can use in order to circumvent back propagating through the solver. I don't think we'll have time to kind of go into the very details of exactly how this adjoint method works. You can directly use that with the library, but if you're interested in kind of the math behind all of that and why it works, the resources that I've found helpful are first, the original paper talks about it well, but I also really recommend these course notes, and I specifically linked sort of the part that talks about getting the adjoint for an ODE. You don't need to know all those details to know how to use the library and sort of train a neural network, but sometimes I think it's helpful to know the details behind what's going on. So now let's kind of implement the different parts of this neural ODE. So, sorry, is there a question? All right. So let's begin by just defining what we mean by the ODE, and this is going to be like a class that we can repurpose when we're implementing both our ground truth ODE, which we'll just use to like simulate some example data to generate solutions and like data points for training, and we'll also use this later to construct our neural differential equation. So now it's going to be like a trainable object that we can try to fit to our data. So I approached this by just defining an ODE class on top of the like PyTorch's like nn.module. So the key kind of method here is that we just need a way to solve the ODE. So you can specify the type of solver that you want to use. The Torch DiffEq library includes several options, and we're just going to stick with this, the Dorman-Prince method just for this tutorial, but you can find kind of a list of the available solvers there as well. Here I've included an option for either using the adjoint method or not. If we're, if we're not back propagating through anything, we don't have to worry about using this adjoint method. So particularly if our model is not something trainable, like our ground truth differential equation, then I have this option here that, you can set this to false and never use the adjoint method because we don't need to worry about it. And then finally, sometimes, especially when we're dealing with like scientific problems and physical systems, we might care about the precision. We might need to, use like a more precise representation of things. So you can specify that here if maybe float 32 is not good enough for the integration. So those are just kind of like the basic inputs here. And the one method that we care about is the solve method, which will essentially just integrate that ODE that we've defined. So when we're training, we want to retain all the gradients so that it can backpropagate and update all the weights. So we'll use this method here when we're training, but when not, we can just turn on like torch.nograd, so we don't have to worry about retaining any of the gradients during that process. And this is just specifying some tolerances for the integrator, which again, you can modify. I've just kind of set these to the defaults for here, since that's good enough for this example. So once we've run that cell, I'm just going to introduce the example differential equation that we're going to be solving, and we'll actually repurpose this for both the neural ODEs part and the pins part, which will be part 2. So it's going to be the same equation, and I think it's kind of like a simple enough example to illustrate both of these points. So this is the Fisher KPP PDE. Essentially, it has like this reaction term and a diffusion term. So R is some kind of a reaction constant and D is a diffusion constant. So the way that we're going to implement this for the purposes of the neural ODE is first, I've just picked some initial condition here. This can be anything, but I've just picked a class of functions that we can use to simulate different initial conditions for this equation in order to generate a variety of trajectories with which to train our model. And then in order to implement this numerically, we're going to discretize this over some kind of a spatial grid. So here I've chosen n as the number of kind of discrete grid points. And this converts the PDE into a system of ODEs, where J is like indexing which of the grid points that we are centered on. So with this kind of machinery in place, let's implement, using our ODE class, let's just implement the Fisher KPP PDE, I guess, but system of ODEs using that same class. And now this is not yet a trainable model. This is just going to use the same class, but it's going to be something that we can explicitly solve. So to define this ODE, the few arguments that we need to specify is that discretization of our grid and also the length of the system. So just the like spatial length over which we're discretizing, which is just one in this case. And then we have the reaction and diffusion constants. So those are the main parameters. And within this init, we're going to specify the functions that control the reaction term and the diffusion term. So very simply, this is the reaction term where we have called y our row here. Just apologize for the difference in variables, but yeah, just keep in mind that y here is actually the variable that we're going to be solving for. And then finally, for the diffusion term, we can actually implement this using a convolution. So for instance, you'll notice here that we're kind of looking at the cell ahead, the cell that we're centered on, and the cell behind. And that looks like a convolution kernel with weights 1, -2, 1. So we're simply going to implement that as like a kernel with those same weights. So we'll use the PyTorch conv1t function in order to implement that. And since we're not training this, we can immediately just set this model to like evaluation mode. So this next function is simply implementing that class of initial conditions that we want. So we can pick some values for those parameters, A, B, and C, that kind of control the family of functions that we're using for the initial conditions. But this can be anything. So this is kind of like up to what initial conditions are appropriate for your system. So this is kind of arbitrary in this case. And then finally, we have the forward method, which is just telling us it is the description of the differential equation. So it simply needs to return dy dt, which we know is just the sum of the reaction and the diffusion terms. I want to just pause here and see if there are any questions about that part. Okay, if not, then let's just integrate this again using our methods for some set of parameters. So here we've chosen 20 discrete points. We're going to generate 100 different trajectories. So we have 100 different initial conditions, which we instantiate here. And then we're going to numerically integrate this up to a final time of 10 with increments of 0.1 in time, at which we choose to evaluate the solutions. And this is going to essentially set up what our ground truth data is in this example. So I've put in a little bit of code here that you can use to plot different initial conditions, and trajectories, that is. So this is like the 0th one. Let's plot this one. They're all, by nature of the chosen initial condition, they're all kind of just like shifted periodically. So relatively simple example here. Okay, so now let's actually implement what the neural ODE would be, assuming that we don't know the Fisher-KPP equation, and all we have instead are these trajectories and this solution space here that we've generated. So one thing we can do, I wanted to illustrate the kind of flexibility that one might be able to introduce into this model. So you can model everything with like a single big feed-forward neural network. Or if you have some knowledge about the system, you could think about decomposing it in a way that kind of reflects that existing knowledge. So for instance, we could try to model this equation as a sum of neural networks, where one is theoretically going to try to model the reaction term, and the other one is going to try to model the diffusion term. So we'll implement them with kind of that prior knowledge in mind, but without knowing exactly what those terms should look like. And so I've used theta and phi to represent the trainable weights of each of those like subnetworks for our big neural network. So in order to implement this, this is a relatively simple model that we're using. So there's really only two kind of parameters for the architecture of this neural network that we need to think about. So I've just included one parameter for the hidden dimension of the reaction network, which we're going to just model as some feed-forward neural net. And then I've also included a kernel size, since we're going to model the diffusion network as some kind of a convolution. So those are the only like hyperparameters in this model, but obviously things can get much more complex for more realistic problems. And so basically here, just kind of in parallel with how we defined the ground truth equation, we're going to have a reaction term, which is here just a chain of dense layers and an activation function using our specified hidden dimension. And then a diffusion term here, which is just some convolution where now the kernel is a trainable function.
Hey, Nina,
Yep.
from the chat, is there a reason to use a convolutional net here?
So the only reason here is that we're kind of assuming that we know we have a diffusion component and that that might be something that could be modeled with convolution. That's typically kind of has the characteristics of a convolution when we discretize it numerically. But in principle, no. If you have a big enough neural network, like a big enough just feed forward neural network with complex enough activation functions and things like that, uh, you can put that in too. So this is just a choice we made here, but it's not a requirement. Okay, yeah, thanks for the question. So the final component of this is, again, just the forward method, which is telling us what the differential equation is. So again, it's just the sum of our now trainable reaction term plus our trainable diffusion term. And you might already notice that this is a sum. Clearly, these are not necessarily going to be easily separated by the neural network. It doesn't know, it won't immediately know that the equation can be separated in this way. So that's something that we'll look at when we see the solution. But even going back to the equation, you'll know that here we have like the rho j terms, but there is a rho j term here as well, and there's no reason that that term couldn't somehow get absorbed in here, or there could be a blending of those terms. So despite our efforts to kind of decompose the problem in this way, it's not going to be a perfect decomposition. We can't expect that of this type of network and the structure of the architecture, but we could, see other motifs that make sense and help us to reason out about what the true equations should be. So with that in mind, let's just instantiate this neural ODE now. So here we're calling that like an ODE, and we're going to create some optimizer. Here I'm using the Atom optimizer with a learning rate of 1e-3, and then we'll just specify the path to save this model. So as kind of a preview for what we expect from training this network now, so the main parameters that we care about are the maximum iterations that we're going to train, which we can set it to however long it takes to kind of converge and get a good solution. I will say that this type of approach differs from maybe the conventional way we think about machine learning, where like we're pre-training on some data that like some large amount of data, and then we're applying the model to some entirely different data. Here, instead of that, we're actually kind of fitting this model to a very specific data set. So the conventional ideas of like early stopping, like thinking about where, the validation set kind of tells us, oh, we've trained this enough, otherwise it's going to overfit to the training data. Uh, they're not as applicable because we just really want to get a model that fits this data set well, and that we can then go in and analyze to understand, okay, does this differential equation obey physical laws that we care about or that we might know? So these max iterations can be quite large until convergence. We have two kind of batch terms. You're probably familiar with like a batch size, like when you mini batch images or data that you pass into a neural network. This is going to correspond to like how many trajectories or how many initial conditions we sample in a single training in a single batch of training. But we also have another dimension in this case, which is time. So we don't have to pass the whole trajectory into the model at once. We can actually just like get a window of that's like a chunk in time from a single trajectory, and so we can batch it up that way too. And so that's why we include two kind of batching options for this. And we'll checkpoint the model at several like intermediate points to see how the training is progressing. So I did put in an animation of one example, like training history during when I was testing this out. So here is what one example trajectory should look like. And here in the middle is kind of the current prediction of that neural network in being able to, when numerically integrated, recover that particular trajectory from a given, the same initial condition. And then over here is our plot of d rho dt as a function of rho, which hopefully, we should see that this prediction that's given by the neural network, we're essentially just plotting the function that that neural network represents. We'll see that it kind of approaches the true function for that as we train. So if you would like to train the model yourself from scratch, that can be done through here. So this kind of set of code is just to create the like the checkpointing things that we need. So I wanted to create these plots, so I created some of these vectors that just allow us to explicitly evaluate at certain checkpoints and save that. So that's mostly just to be able to create this animation. But the main part that you need to run would be this like training loop. So this pretty much follows the same process as training any other type of neural net, but we're basically, we zero our gradients, and then we're going to take a batch. And as I mentioned before, we can batch both in the initial condition dimension and in the time dimension. So this get batch function that again is in the utils is just handling that type of batching for us. So you can take a look in more detail, but it's nothing more than kind of just chunking up our data in two different dimensions instead of one. And that gives us a batch of times, a batch of initial conditions, and a batch of the trajectories corresponding to those initial conditions. And so, as we saw before, we're going to use our neural ODE and solve it for that set of initial conditions and times to get a prediction for what the trajectory should look like. And then we'll use the mean squared error loss to compare those with the true trajectories from that sampled batch, and then backpropagate. And this is, again, just saving some checkpoints so that we can make a nice plot. So if you run this, you'll see, I'm not going to run it for a lot of iterations here, but you should see kind of the loss start to go down. I'm going to stop it here. And for the remainder of this, I will go ahead and load in a pre-trained model to show you the results. But once you're training this, you can go ahead and plot sort of the loss curve. It's not trained very far yet, but you can plot this out and you can save the current state using these cells. And finally, once you're happy and you've fully trained, you can go ahead and save an animation if you'd like to recreate the one that was used here. The final step that I want to show you for this is at inference time, what are now the capabilities of the trained model? Because now theoretically, we've trained a model here. It's this pre-trained model that can reproduce the data that we showed it during the training time. But what can we do beyond that? Like, how useful is this model? So I think the main use for the neural ODE now is that we've learned the differential equation. So in theory, we can apply it to cases where we have different initial conditions, maybe that were like too difficult to prepare or observe in the real experiment, but we want to see how a system with those initial conditions might evolve. And also, because this whole thing is based on just integrating a differential equation, we can theoretically go like extrapolate much further in time and much more kind of stably and reliably than if we're like using some autoregressive model that's just predicting one step from the history. Because this is actually, it's based on doing a numerical integration. So as long as the equation is stable enough, we should hopefully be able to integrate it. So here I've just shown an example where now we've generated some different set of initial conditions by modifying like the A, B's, and C's in our initial condition function. And then I've also increased the final time that we are simulating to from 10 to 20. And this is just, again, like a helper function I've used to just make this complete plot. But you can see from here that, now, even though it was never shown this particular initial condition, and also it never saw something as far out as, 20 units of time in this example, it can still get like a good prediction in that case. So I would say it, at least in practice, like where I've used it, sometimes we have experiments which, the sample will degrade if we continue to run the experiment, but we want to know what's going to happen in the future if we could. So maybe we can model the data that we have available with a neural ODE and then evolve that ODE further in time so we know we can kind of get an idea of what's going to happen going forward. This concludes the neural ODE part, so I want to pause here and see if there are any questions for the neural ODEs. Okay, and if not, then let's go ahead to part 2. This part will be a little bit shorter because we've built a lot of the machinery up, but
Nina,
yep.
question from the chat. During the training, the in time evolves the system at each iteration, right? If so, can't you use, say, 10 seconds of time evolution to train the in and then the next 5 as validation?
Oh, that's a great question. Yes, you could. You could do that. Yeah, certainly, if there's a good way to um, yeah, chunk up your data like that, that that could be done. The only thing I was trying to say with kind of like not needing to do early stopping and things like that is we're not worried about overfitting to the data in this case because we are just trying to learn the best possible model. But if you do feel like maybe you have quite different trajectories, and so if you have one example that you're fitting to a little bit more, um, that could make the model kind of generalize less across different initial conditions or trajectories. So in that case, yeah, I think doing something like this where you do have a validation could be really useful. So yeah, thank you so much for the question and the comment. All right, so then let's go on to the physics-informed neural nets. So in this case, we're now going to assume that we actually know this differential equation. So like we have, um, we in this case are thinking, oh, this is actually a really hard equation to solve. It's not, but for the purposes of this, we're gonna say like we cannot solve this numerically. So there could be, scenarios or initial conditions where this might be really complicated. So we're going to treat this as a known and then hypothesize that we have a neural network that can directly approximate a solution to a specific initial condition. So that so that is kind of a limitation, I guess, of this is that here we're not going to be able to generalize, but we're going to have other benefits that like neural ODEs don't. So they're really like the use cases are pretty different. So this is more like a compare and contrast between appropriate use cases for these approaches. So the way that we can train the network to represent the solution of this PDE without being able to numerically integrate it is we can write the loss in a way that enforces that PDE. I think that's kind of the main trick behind this. So we know that neural networks are kind of like fully differentiable with respect to these inputs, t and x. So that means that we can use automatic differentiation to differentiate them with respect to those things. So we can write like df dt equals, and then plug it in like everywhere that we see rho in this equation. And we can say we expect that this neural network is also going to satisfy that equation. And we can then express this as a loss. So here we're using a mean squared error just to say the left-hand side equals the right-hand side. And we have to sort of evaluate this at some points, but they can be randomly sampled in our domain. We're kind of unrestricted. We just wanted to enforce this equation, but we don't have to care exactly which t and x we use as long as they're like in our domain. And then additionally, we said that this solution has to correspond to a specific choice of initial and boundary conditions. And so these are also used as constraints that we enforce in the loss. So for instance, the initial condition, which is that function that we had before, we just calling it row 0 here, but it's some function, and we're going to say that at time 0, our network has to match what that is. And we're going to write another mean squared error and add that to our loss. And then finally, for the boundary condition, here we just assume that we have periodic boundaries. So we're just going to enforce that the neural network at x equals 0 is the same as that, has the same value as that at x equals L, which is the other side of our domain. And then all of those three terms just get added up to create our full loss. And this is why it's called kind of physics informed, is that all of the physics is really baked into the loss function, and that is what's used to determine how the neural network is trained. So as before, we are going to implement a neural network, but now it's going to model the solution to this particular equation. And we have a few parameters that we can specify to construct the architecture. Here, again, this is completely kind of flexible, but we have some hidden dimension, and here we've also set a number of layers since we're going to model this as just a fully feed-forward neural net. So those are the hyperparameters that we've allowed. And then in this case, since we are modeling a known differential equation, we fully specify it by stating what R and D are. So we know these values. Okay, I think to make it more kind of complicated or general, there are examples where you could kind of adapt this and have more unknowns. You could have some like trainable parameters in here as well, even, but enforce the general like form of the equation if you wanted to make it more complex. But here we're just going to keep R and D as known values. And so as before, we're just constructing a neural network here. Just all this is doing is just building like a chain of dense layers with tanh activations for however we specified our architecture. And again, we have a function that's going to specify an initial condition for us, since we need to know it. This needs to be fixed. And then these two functions are kind of the unique ones for this for the pin case. So we're going to have a function here to calculate the PDE using automatic differentiation. So whenever we evaluate our neural network, so we call the forward method, which basically gives us the value of y at a particular t and x, we're going to use automatic differentiation to compute first the double derivative with respect to x, ultimately, because we need to do that for the diffusion term. So we take one derivative with respect to x, and then we take a second derivative with respect to x to get that term. And then we're also going to take a derivative with respect to time. And then we're going to return that dy dt term, which is left-hand side, and then we're going to return the right-hand side, which is the reaction term plus the diffusion term, which has this double derivative in it. So in that way, we kind of leverage the inherent capabilities of neural nets. And then like we used here already, actually, this forward method is actually just returning the solution. So in this case, we have two different inputs, t and x. In our very simple implementation of the architecture, we just kind of concatenate them and we pass them both together to our neural net. So you can see that the initial, the first layer of our neural net expects two inputs. Those are t and x. And then it's going to return a single output, which is the value of y at those points. And so that's all we need to kind of build this neural net. Here we've instantiated it. You can see it's just a bunch of linear layers. And just as before, I've created kind of this preview of what we should expect to see when we train it. So again, we have some maximum iterations that we want to train for. We'll have a batch size, but here the batch size means those random points that we're sampling in the interior to enforce our differential equation. So this batch size is usually huge because we want to sample kind of densely, if we can, the domain to try and capture the differential equation. And then we'll checkpoint for some intermediate steps. So you can see here the evolution. It's kind of different from how the neural ODE was trained. It doesn't look like anything is happening for a while. And then suddenly around here, it kind of like locks into the solution. And I think that the loss landscape for pins can be a little bit tricky sometimes. I'm not like an expert in this field, but I've seen some papers kind of discussing how to make that lost landscape a little bit smoother and regularize things better. Here, I haven't done anything fancy with it. It's just, the bare bones implementation. But you can imagine that, like when I was training this, I kind of got discouraged initially, but I was just holding out, and then finally it did find the right solution, but it took a little bit of time. So in order to set up the training for this, the only reason that I have discretization here is that when we sample the boundary and initial conditions, I'm just going to like sample those at discrete points always, not random points. So I've created, these discrete vectors for t and x just to evaluate at those specific points. So for instance, for the initial state, which is at t0, I'm going to sample the initial condition at 20 points at the initial state, always. And then for the boundaries, we, again, I wanted a fixed number of time steps at which to sample the boundaries, so just picked 10 and to create the boundaries that we're going to use for the boundary condition constraint. And then, as I mentioned before, the batch size for sampling in the interior for our most important equation, which is the one enforcing the PDE, it can be quite large. So this is saying we're going to sample 1,000 pairs of t and x at each iteration in order to evaluate that loss. And again, we just have some things needed for the checkpointing, which you can kind of customize. I just saved them for that particular animation. The most important thing is the training loop here. So just to kind of walk through it, it's mainly defining those 3 losses, evaluating them, and then backpropagating. So for our initial condition loss, we're going to take the model that we've instantiated and evaluate it at time 0, which is just 0, and get the predictions for y there. And then we use the mean squared error to enforce that that matches our initial condition, which we predefined above. Similarly, for boundary conditions, we'll evaluate our pin at the 2 boundaries, and then we'll enforce that they match with a mean squared error. And then finally, and this is sort of the main part, is we're going to take a random sample of times and positions of that batch size. So this is just a random sample in our domain. And then we're going to evaluate the PDE. So we take this, remember our PDE function returned the left-hand side and the right-hand side. So we're going to just be unpacking those and then trying to get them to match using a mean squared error loss. And this all gets summed up into our total loss, which we again just backpropagate and optimize. So I'll run this again, just to see that hopefully the training starts to, like we see the loss start to improve. As I said, it's a little bit, it doesn't look like it's improving right away necessarily, but it did ultimately get there. And you can plot, this is just the first 10 steps, but I've pre-trained the model for like 20,000 steps. So we have a pre-trained one that's available also in that repo that you can load. And just like for the neural ODE, what's our use now for like this model? Besides the fact that, it's now given a solution for a differential equation that we couldn't have otherwise integrated potentially, what can we use this model for that maybe goes beyond that? So I think the main thing here is, unlike the neural ODE, where we trained it with a specific discretization of the spatial domain, and that's how our model is built. It's baked in, and we cannot, necessarily like sample more finely than that. Here, we don't have any kind of implied discretization. So we can sample, for instance, every 50 points, like create a grid of 50 points in our domain instead of the 20 that we used at the initial condition. And so just to show you that example, here I'm going to integrate the real ODE at this finer resolution, and then further going to extrapolate and integrate this pin, not integrate the pin, sorry, evaluate the pin at that finer resolution as well, and compare those two. And so you can see here, we can get, the finer resolution of these points that matches pretty well what the original equation was. So that concludes the pin example. Pause here and see if there are any questions about this or any other part of the notebook. And if not, I just want to thank you all for joining this tutorial, and hopefully it was useful.